Welcome back to my channel. Today's video focuses on algebraic manipulation method. This method is useful in finding values of expressions given some equations, but this one usually involves rearrangement of terms rather than finding the values of individual variables. Alright, now how do we do algebraic manipulation? Let's have some examples. Example 1. If 2x plus y plus z equals 36, x plus 2y plus z equals 40, and x plus y plus 2z equals 32, find x plus y plus z. If you're going to find the values of x, y, and z individually, then we would have a lengthy solution. However, notice that if we add all the equations, let me write them first. We have 2x plus y plus z equals 36, x plus 2y plus z equals 40, and x plus y plus 2z equals 32. Now notice that if we add the three equations, we actually have 4x plus 4y plus 4z equals this is 8, this is 108. Alright, now notice that if we divide both sides by 4, we get the desired expression x plus y plus z. So let's do that. We have x plus y plus z equals 108 divided by 4, and that is simply 27. Alright, let's have another example. Let x, y, and z be real numbers so that x plus y times y plus z equals 36 and x plus z times x plus y equals 4. Compute y squared minus x squared. Notice that in the desired expression, there are only two terms. So this means that, or this is an indication that we might try to subtract the two equations and then hope that some of the terms will cancel, right? So before we do that, let us try to expand first the equations, because the left hand sides of the two equations are in factored form. So let's copy first. We have x plus y times y plus z equals 36. Alright, so another is x plus z times x plus y equals 4. Let's have this first. This is equivalent to xy plus xz plus y squared plus yz equals 36. The other one is equivalent to x squared plus xy plus yz, plus xz, so that's xz. Alright, so plus yz equals 4. Now, if we multiply both sides of the second equation by -1, we will have this equivalent equation. And then if we're going to combine this one with the first equation, we will actually cancel xy, because this will be negative already. What else? We cancel xz, and then we cancel yz. Okay, so what remains now is y squared minus x squared equals 32. And take note, y squared minus x squared is the desired expression. So the answer we're looking for is 32. Let's have our third example. Suppose a and b are two numbers such that a squared plus b squared plus 8a minus 14b plus 65 is equal to 0. Find the value of a squared plus ab plus b squared. Alright, let's copy first the given equation. We have a squared plus b squared plus 8a minus 14b plus 65 equals 0. Alright, notice that we have a squared and 8a. We also have b squared and negative 14b. Now, is it possible to form perfect squares? Actually, it is possible. Now, if you rearrange in this manner, in particular, we have a squared plus 8a plus b squared minus 14b plus 65 equals 0, then it is clear that we can actually form perfect squares. Take note that we can just add 16 to a squared plus 8a, and then we have now a perfect square. We can also add b squared we can also add 49 to b squared minus 14b to get a perfect square. So how do we do that? We can actually split 65 into 16 plus 49. So we have a squared plus 8a plus 16 plus b squared minus 14b plus 49 equals 0. Now we can factor. So this one is the same as a plus 4 squared. The other one is the same as b minus 7 squared. So we now have this equation. Now, each term is a perfect square. So this means that for any real values of a and b, each of these terms is greater than or equal to 0. However, the sum of the terms is 0, which means that the only way for the sum to be 0 is when a plus 4 is equal to 0 and b minus 7 is equal to 0, which means that a is equal to negative 4 and b is equal to 7. Now we can find the value of a squared plus ab plus b squared. That is just negative 4 squared plus negative 4 times 7 plus 7 squared. This is equal to 16 minus 28 plus 49. Okay, so that must be equal to 37. And that's our answer. Next example. Suppose x, y, z are real numbers such that suppose x, y, z are real numbers that satisfy x plus y minus z equals 5, y plus z minus x equals 7, z plus x minus y equals 9. Find x squared plus y squared plus z squared. Let's list down first the equations. We have x plus y minus z equals 5, y plus z minus x equals 7, and z plus x minus y equals 9. Alright. Now, let us add the equations and let's see what happens. So if we add the equations, we will actually have x plus x, that's 2x, minus x. So I'll just add this one first, this part. Okay, so we have 2x plus 2y plus 2z, and then we have minus x minus y minus a z. So this is 5 plus 7, that's 12, plus 9, 21. Alright. Now, we can subtract. We have x plus y plus z equals 21. So we could have just combined all the terms earlier. So we have x plus y plus z equals 21. But we need x squared plus y squared plus a z squared. Take note that the first equation can be written into x plus y equals a z plus 5. Now, what do you notice about this one? There is an x plus y, right? Now, if we replace x plus y here by z plus 5, then we can just solve for z, right? So let's do that. So let's replace x plus y here by z plus 5. Z plus 5. So we have z plus 5 plus a z equals 21. So we have 2z. Transpose the 5. That gives us 21 minus 5, 16. And if we divide both sides by 2, we get z equals 8. Okay? So this is the value of z. Let's box that. Now, using the same process, we can we can convert the equation into y plus z equals x plus 7. Okay? And we can also replace, so using again x plus y plus z equals 21, we can replace y plus z by x plus 7. So this one becomes x plus 7 equals 21. So we have 2x equals 21 minus 7. That gives us 14. Divide by 2, x equals 7. So x equals 7. Now we just need to find y. So instead of doing the same process with the third equation, we can just go back to the equation x plus y plus z equals 21 and plug in x equals 7 and z equals 8 to find y. Alright, so we have again x plus y plus z equals 21. This is 7 plus y plus 8 equals 21. So this is y plus 15 equals 21. So y equals 6. Now we can find x squared plus y squared plus z squared. So this one now, let me use another color. So this one now is 7 squared plus 6 squared plus 8 squared. That gives us 49 plus 36 plus 64, or simply 149. So this is the required value for x squared plus y squared plus z squared. Okay, so let's have our next example. Given a minus b equals 2, b minus c equals 4, find the value of a squared plus b squared plus c squared minus ab minus bc minus ca. There's actually an algebraic identity. This is quite popular. So if you know this identity, it is just this identity involves this expression. This is actually equal to 1/2 times a minus b squared plus b minus c squared plus a minus c squared, or c minus a squared. That is just the same. Now, I don't like to directly give the formula without explaining why it is true. So I'll show you first why the given expression is equal to the expression in color red. Okay, so let's do that. Okay, I'll erase that first. So we'll do that again. So I'm going to show how it is being derived. Alright, so I'm going to write first the given expression. So we have a squared plus b squared plus c squared minus ab minus bc minus ca, or ac. Now, take note that this expression is the same as 1/2 times 2a squared plus 2b squared plus 2c squared minus 2ab minus 2bc minus 2ca. Now, I'm going to rearrange the terms inside the parentheses. Take note that the terms can be rearranged into a squared minus 2ab plus b squared plus b squared minus 2bc plus c squared and a squared minus 2ac. So I'm just going to write 2ca into 2ac, that is just the same, plus c squared. You can check that the number of copies of a squared, b squared, c squared, and the other terms in this new expression is the same as in the original. Okay, now we have perfect squares. So I'm going to write this one into a minus b squared, b minus c squared plus a minus c squared. Okay, so we have shown why the original expression is equal to this expression. Now let's solve the problem. We already have a value for a minus b and b minus c. However, we don't have a value for a minus c. Now, if you add the two given equations, you actually get a minus c, right? So let's do that first. So a minus b equals 2, b minus c equals 4. So if you add this, we cancel b, right? So we have a minus c equals 6. Now we can plug in the values. So 1/2 times 2 squared plus 4 squared plus 6 squared. This is equal to 1/2 times 4 plus 16 plus 36, which is equal to 1/2. That's 4 plus 36, that's 40, plus 16, that's 56. So 1/2 times 56, that's equal to 28. So this is the final answer. Let's have example number 6. Let x and y be real numbers such that xy equals 4 and x squared y plus xy squared equals 25. Find the value of x cubed y plus x squared y squared plus xy raised to 3. Alright. Notice that this equation, the left hand side of this equation can be factored. This expression can also be factored. Okay, so let's factor the left hand side of the given equation first. Let's see what happens. So x squared y plus xy squared equals 25. So this is going to be, the common factor is xy. So xy times x plus y equals 25. But we already have a value for xy, right? So let's plug in xy equals 4 here to simplify the equation. So this one, we have 4 times x plus y equals 25. So we have x plus y equals 25 over 4. Alright, now let's factor the given expression. So the given expression, x cubed y plus x squared y squared plus x y cubed, this is equal to, okay, so the common factor is xy, so this is equal to xy times x squared plus xy plus y squared. And now again we have xy equals 4, so we can just replace the xy's here. So we have 4 times x squared plus 4 plus y squared, right? However, we don't have a value for x squared plus y squared, but we can write this expression into x squared plus 2xy plus y squared minus 2xy plus 4, right? So this is going to be 4 times x plus y squared minus 2xy plus 4. Now we can plug in all values needed. Again, x plus y is 25 over 4, so we have 4 times 25 over 4 squared minus 2 times xy. Xy is 4. Okay, so let's simplify this. This is equal to 4 times 625 over 16 minus 8 plus 4. Alright, this is equal to 4 times 625 over 16 minus 4. If we're going to distribute, we will have 625 over 4 minus 16. Okay, so let's write it here. So we have 625 over 4 minus LCD is 4, so we have 64 over 4. Finally, the answer is 561 over 4. Alright, now let's have example 7. Find all possible values of x cubed plus 1 over x cubed given that x squared plus 1 over x squared equals 7. Notice that in the given expression x cubed plus 1 over x cubed, we can write 1 over x cubed as 1 over x raised to 3. Now, that's sum of cubes. So it's helpful here to apply the sum of cubes formula. Recall that the sum of cubes formula is given by a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Alright, now let's do that. So if we apply that one, the right hand side here becomes x plus 1 over x times x squared minus x times 1 over x because our a here is x and b is 1 over x. So this is plus 1 over x squared. Now let's simplify. We have x plus 1 over x times x squared. This is minus 1 since we can cancel x, and this one is 1 over x squared. So I'm going to rearrange this into x squared plus 1 over x squared minus 1. Take note, we already have a value for x squared plus 1 over x squared, and that is 7. However, we don't know yet the value of x plus 1 over x. So what are we going to do now? Look at x squared plus 1 over x squared equals 7. Is it possible to create a perfect square in the left hand side? Now, let's copy x squared plus 1 over x squared equals 7. Let's manipulate the left hand side. Recall that the perfect the square of the binomial a plus b is equal to a squared plus 2ab plus b squared. We can apply this one in the left hand side, because we can write the left hand side here into x squared plus 2 times x times 1 over x plus 1 over x squared, but we need to subtract 2 times x times 1 over x. Alright, now the first three terms constitute a perfect square, because we can write this one into x plus 1 over x squared. Okay, and the following term is just minus 2 because we can cancel x. So this one is equal to 7. And so we have x plus 1 over x squared is equal to 9. Now if we get the square root of both sides, we get that x plus 1 over x is equal to plus minus 3. So we have 3 possible values for x plus 1 over x. Now we can solve the given expression. So this one now is the same as plus minus 3 times 7. X squared plus 1 over x squared is 7. We have minus 1. So that's equal to plus minus 3 times 6. So there are 2 values. So that's 3 times 6, positive 18. The other one is negative 3 times 6. That's negative 18. Alright, let's have our last example. We have given x over x squared plus 3x plus 1 equals a, where a is not equal to 0, express x squared over x raised to 4 plus 3x squared plus 1 in terms of a. Let's copy first the equation x over x squared plus 3x plus 1 equals a. What I'm going to do now is multiply the numerator and denominator by 1 over x, because we will come up with a certain expression that is very familiar and is related to a perfect square. So let's multiply the numerator by 1 over x and then the denominator by 1 over x as well. So if we do this, we get 1 over x plus 3 plus 1 over x equals a. And then I'm going to rearrange this into 1 equals a times x plus 1 over x plus 3, and then divide both sides by a. So we get 1 over a equals x plus 1 over x plus 3. And finally, transpose, we get x plus 1 over x equals 1 over a minus 3. Okay, now let's box this one. Now I'll do a similar process to the given expression. So we have x squared over x raised to 4 plus 3x squared plus 1. So if we multiply this one by 1 over x squared, we get 1 in the numerator. We also multiply the denominator by 1 over x squared. We get x squared plus 3 plus 1 over x squared. Okay? Now, that is why I multiplied the first equation by 1 over x over 1 over x, because here in this expression, we will come up with x squared plus 1 over x squared, which we can turn into x plus 1 over x raised to 2. Okay, and we will be able to use the first result of our manipulation. Alright, now take note that this is the same as 1 over x squared plus 2 times x times 1 over x plus 1 over x squared, but we need to subtract 2 times x times 1 over x. Okay, so we still have a plus 3 here, right? Now we can factor the first 3 expressions to get x plus 1 over x squared, and then cancel the x here, so we have minus 2 plus 3. That is simply so we have 1 over x plus 1 over x squared plus 1. Now we will be able to use now the 1 over a minus 3, the 1 over a minus 3 expression here, but let's try to also find the LCD to simplify this. So this is going to be 1 over a minus 3 squared. Again, I'm replacing now x plus 1 over x by 1 over a minus 3 plus 1. So this is 1 over this is going to be 1 minus 3a over a squared plus 1. Alright, and so we have what? We have 1 over 1 minus 6a plus 9a squared divided by a squared plus 1. And take note, a is the same as, 1 is the same as a squared, so I can just write this into a squared over a squared. Again, 1 is the same as a squared over a squared. So if you combine the fractions in the denominator and then simplify further, we must get a squared over 10a squared minus 6a plus 1. Alright, so this is now our final answer. If you've learned something from my video, please share, and thanks for watching.